let this represent our loop of current. And for just today, for this moment, let's not get too bogged down with the fact that how does the current get into the loop? It could just be that I have a wire like the wires you guys made for your motors, something like that. And we're kind of ignoring these parts or these contributions to the magnetic field and only being concerned with the loop itself. Does that make sense? You guys follow what I'm saying? So we are missing how did the current get into the circle part. But don't get too bogged down with that. As with anything else, edge effects, stuff like that, we're just going to kind of ignore those portions of the magnetic field. And you might find that ignoring those makes real sense when you start making some of these things, especially like when we made our motor cores. When we made our motor cores, remember how the wires went off perpendicular to the loops? Well, remember, if a particle is traveling directly towards you, do you detect a magnetic field from that particle moving towards you? Well, the same would have to be said for a current directed directly towards you. So if you made your motor core like this, with the wire going directly towards the center of the circle, and then had a hard right angle when the loop began, those two entry wires didn't contribute to the magnetic field at the center of the circle because they can't. The cross product would work out to be zero. And prove it to yourself. I, ds, cross r hat. Just this part is all you have to look at to realize that if I is going towards the center of the circle and your r is also pointed towards the center of the circle, that's a sign of 0 degrees. And therefore it would not contribute to a magnetic field at the center of the circle. There's certainly a magnetic field around the outside of this wire as it gets towards that loop, but there's nothing contributing to the center of the circle. For us, we are interested in the magnetic field being produced at the center of this circle. That's our goal. So for the time being, we're looking top down on this monstrosity. I would hope that you could take your right-hand rule and using the curl rule, figure out whether the magnetic field at the center of the loop is into the board or out of the board. So let me erase that because I didn't test that ahead of time. And let's use our right-hand rule and let's go around the loop and see what we get for our contributions to the magnetic field. So again, I want to emphasize that you should take a moment using your right-hand rule and realize that there is a magnetic field produced in a circular fashion around this wire, and it is into the board on this side of the wire and out of the board on this side of the wire. And that's true everywhere around the wire. So same kind of idea here and here. That will contribute to a magnetic field, a net magnetic field into the board at the very center of the circle. Now, we're going to be firing up Biot Savart. So there is a small contribution to the magnetic field that will be equivalent to a complicated set of constants times the current that's in the loop times a piece of arc length, a length, compared with the direction to our point of interest. Right? R hat points to our point of interest. Our interest is at the center of the loop. All divided by how far away we are from the center of the loop squared. All right, so these are all the pieces necessary that we're going to assemble to create the integral that will give us the magnetic field at the center. Now, a lot of these are no big deal, and we've handled some of them, but let's go ahead and identify on our loop a piece of the arc. So I'm going to say from here to here is our ds, a piece of arc length, and it is length ds long. That all okay? All right, from there, I'm going to draw an arrow that points to our area of interest. Right? This is our location of interest. Right? This represents R. It is a vector that points from ds to the point where we're trying to figure out the magnetic field. And the first thing I'm going to notice before we go any further is that when I compare every possible ds to every possible r, ds and r are perpendicular to each other everywhere in the circle. Right? ds is an arc length. It's going to have a direction that is tangent to the circle, and r points towards the center of the circle. Are we all good with that? So I'm seeing two faces that suggest they're not okay with it. So ds, by definition, points in this direction. Right? It is a piece of the arc and is therefore tangent to the circle. And we're looking for the magnetic field at the center of the circle, which will have to be a vector that is radial or along a radius. And therefore, these two have to be at a right angle. So I'm dealing with the cross product first, and in dealing with that, I'll rewrite my Biot Savart to take into account the idea that the ds cross r will produce a sine of 90 degrees for every single contribution to the magnetic field. So no matter where I am on a circle, ds cross r will have a sine of 90 degrees. Everybody convinced of that? Be convinced by putting that in your notes. Note why I went from the cross product to a sine of 90. Write a sentence so that you don't have to talk to me about that later. You know, this is one of those things that you don't write down and then you ask yourself later, well, why did we do that? It's not like you're going to watch these stupid videos. Nobody does. The average watch time is like a minute and a half. So people aren't, and they go like 30 minutes. So either you're watching it at really high speed or you're the one person who makes it to the end. Now, I've watched one or two of them on really high speed. They are kind of funny. So, but I'm thinking about scratching the whole YouTube channel. But we'll see.
I actually watched those. I watched the rest of them up there, and I checked it every day because I was waiting. I do watch them, I promise you.
Okay. Well, I'm sorry that you watched them. Only because I fear that they are just not very good. I spend no time in the editing room. Hit a button, post it. We'll see. Someday, I want to have like the YouTube physics channel. But there's other people who do it so much better with cool like graphics and really bad jokes. I just don't think I can live up to that level of potential. Yeah.
We had multiple classes. I would watch like the other classes for videos for like mechanics. We had 3.
So we settled on that part. We've gotten rid of the cross product. That helps because there's not much left. The sine of 90 is going to be 1. So, I mean, I wrote it down there just so we had it, but truthfully, it's going to disappear. Let's also handle the comparison between ds and r squared. Can we, at this time, establish that every single piece of wire is the same distance away from the center of the circle? Right? They're all a radius away. So when I'm integrating, r does not change with any ds. That was not true yesterday, remember, because every piece of the wire was a different distance away from our point of interest, so every single ds had a different r. But this time, every ds has the same r. So I'm going to go ahead and collect all the things that are constant for for this contribution. So our constant is constant, I is constant, sine of 90 is constant, and r squared is constant. All of that is constant. All I have left is adding up the length of the loop. Now I'm not gonna stand on circumstance here. We know the length of the loop. If I'm adding up every piece of length of a circle, can we all agree that the whole length of the circle will be its circumference? So I'm going to integrate, and I'm not going to worry too much about the limits here because I have no contributions left that have anything to do with direction or angle or anything. I just need to add up the entire length of the circle. So I will get that the entire magnetic field equals mu naught over 4 pi times I sine 90 degrees over r squared times 2 pi r, the circumference of the circle. We all good? The easiest integral we've done all year, most likely. Now, the truth is, we could have said ds is r d theta, and we could have then integrated this from 0 to 2 pi. Right? We could have done the long way around to show that the circumference is 2 pi r. But are we okay in not doing that and just saying we're adding up the length and get 2 pi r? Because I know College Board's okay with that. All right, sine of 90, 1. R cancels with one of the r's in the denominator. 2 cancels with 4 to give me 2. And pi cancels with pi. So my final magnetic field for the current loop is going to be mu naught I over 2r. So now I beg you to remember what you were supposed to memorize yesterday for the magnetic field of an infinitely long wire. Do you remember? Can you say it back to me? Remember, the negative side didn't matter. That was just an indication of direction. So scrap the negative sign, just give me the size. Where z represents our distance away from the wire and r represents our distance to the center of the circuit. Do you see something here? They differ by only one thing, right? Pi. And the one that is a circle doesn't have pi, and the one that is not a circle does. Do we see that? Yes, commit these to memory. You'll want to. Now, this one, super easy to prove with Ampere's law. Super easy to prove with Ampere's law. This one, impossible to use Ampere's law to find this one. Please, if you're going to memorize something about magnetic fields, these are the things to memorize. Especially since when we learn Ampere's law, we're going to be using it like Gauss's law to figure out the magnetic field in specific kinds of shapes that are useful for storing energy, the solenoid being the most important one. Understanding when we're dealing with a current loop what the magnetic field is tantamount to understanding what's happening. But not a particularly hard one, is it? So a current loop has a magnetic field of mu naught I over 2r. So this is our loop, this is our wire. All right.